In this video, we're going to be working on linear inequalities and absolute value inequalities. So the first thing we need to know is how to represent our answers once we come to them. And what I have across the top here are four different inequalities, both the greater than and the equal to and the greater than, less than or equal to and the less than. Now, when we're talking about graphing on lines, we're used to seeing maybe an open dot and a closed dot when we talk about greater than or less than and equal to. And what we're going to do is we're now going to switch to brackets. Brackets and parentheses are what differentiate whether we talk about greater than or equal to or just greater than, less than or equal to or just less than. So the brackets are what we use to represent our greater than and equal to and less than or equal to, while parentheses, or what I call soft brackets sometimes, are what represent just the greater than or less than. So let's look at, first of all, how we're going to do this on the number line. So we know that if x is greater than a -4, I've got this little number line here, and this means that our numbers are going to be everything greater than a -4. And this is a very shortened line. Obviously, I could have -3, -2, and so forth, and I could have -5, -6 on the number line, but I'm making this a very short number line just for our notes. So we know that greater than means it's going to be everything to the right or everything larger than -4. But when we have an equal to, that means our stop point will be set off by a bracket. In the same way, I know that x is going to be greater than 5, which means I'm going to have everything greater than 5, again on my little mini number line. But this means a soft bracket means, or a parentheses mean, everything up to 5, but not including 5. And in the same way, we're going to do less than or equal to. Less than means less than 6, so it means I'm going to go to the left on my number line, 5, 4, and so on and so forth. But having the less than or equal to means the hard bracket, I kind of missed that 6 there, hard bracket or the squared off bracket here, and it's everything less than, and then when we have just less than without the equal to, we're still going to go smaller or to the left in the number line, but this means I'm going to have the rounded bracket, and I'm going to make that round right there. So the other ways to represent it is in what we call the interval notation, and for the interval notation, I like to use the number line to help me out. Basically, what I want to know is what is the beginning and end of this entire interval. So we notice that I go all the way to infinity as I'm going all the way to the right. But I start at a -4. When everything's greater than, it goes all the way to infinity, and then it starts at 5. But what we do here is we usually use the parentheses and the brackets to represent whether or not it's going to be equal to or not. So the same way here, it's going to be everything greater than or equal to, so that hard bracket or that squared off bracket on the side means that I'm actually going to have a greater than or equal to situation. If I wanted just a greater than situation without the equal to, then I put a parentheses around it. Well, we can never have an equal to infinity because infinity goes on forever, so infinity will always have a round bracket. Always, always, always. Looking at the same thing again, we are doing the endpoints. I'm going to infinity on this side, and it stops at 6. And infinity always has the negative, or excuse me, the parentheses around here. And I said negative because I have to remind myself that we're going into the negative infinity down here. So the less than will include negative infinity, the greater than will include the positive infinity. But this one on this side, it was less than or equal to, so this side gets this squared off brackets. So if it has a squared off bracket, we're equal to. If it has a rounded bracket, it's just the less than. And again, the negative infinity is on the other side. So when we ask for an interval notation, interval basically means the start and the end point. So start point, end point, start point, end point. So if I look at this one, I'm going to skip down here to this problem just for a second. This actually gives me my start point, end point. So I can have 0, 1, 2, 3, 4, 5, and I have a -1, -2. That means that that interval, that graph, goes down to -2, but is not equal to it. And it goes all the way up to 5 and is equal to it. So your set builder notation and your graph should have the same endpoints. I'm kind of trying to darken it in here a little bit. Same thing over here. I'm going to have 0 here, 1, 2, 3, 4, 5, 6. That means my interval is greater than 1, but is less than 6, and it goes in between these two values right here. The other way to represent your answer is in set builder notation, and I've had this set off to the side. Basically, it's a small sentence where we always start out with the definition of x, or whatever your variable is, and then this line. This line means the term such that. So we're saying that all of my set is all of x such that x is, and then we basically include our inequality again. That's a simplified way of doing it, but it's basically defining every value that's going to show up in my set. So this is what it would be for this particular answer here. So if I want to do the set builder notation here, this means that all of x such that x is greater than 5. And it might seem redundant, but it's a nice mathematical sentence for building every value that might be in it. And we can have all sorts of definitions. I could say all of x such that x is less than 6, less than or equal to 6, but excludes 10, or but excludes -2, but excludes this. There are so many ways to represent it, but as we're getting used to the set builder notation, we want the definition of the variable such that, and then the inequality here. So when I'm looking at this problem down here, we've already graphed it, but I want to know what items this includes. Well, this is in set builder notation, is all of x such that, such that x is between -2 and 5. And that's what it happens to be. But if you'll notice, one side has the rounded bracket, so it just means less than. The other side has a squared off bracket, which means I have to include the less than or equal to. So when creating your set builder notation, you need to make sure that you include the appropriate either less than or less than and equal to. So pause the video for a sec and create this set builder notation here. Hopefully this was the set builder notation that you got, because again, the bracket indicates that it's going to be less than or equal to. The rounded brackets or the parentheses indicate that it's simply going to be less than without the equal to. Now in this one, we have the situation where I have all of -infinity stopping at 4. So I'm going to place on the number line at 4. And sometimes we include more information on my number line. But we definitely have the rounded bracket at 4, and we're going to -infinity. So I'm definitely going anywhere to the left. So it looks like this is going to be all of x such that x is less than 4. And again, no equal to, because I have my rounded bracket. This one starts at -3, -2, -1, 0. I can make it up on the number line as much as I want. We start, your bracket again should match everything, going further to the right because we're going greater than. So it's my set builder notation is x such that x is greater than or equal to my -3. Now the next concept is the idea of union and intersection. So what we have is we have this little notation which you might not have seen before. This little hump here is talking about intersection. And what this is asking for is all the values in common. The other side, upside down, looks like a U or union. This wants all values from either set or either graph. So for me, what I like to do is I like to graph one of them, one set, the other set, and then see where either there's the intersection or everything in common. So let's start with graphing this set right here on this number line. Now for my, to make a little bit more organized, what I'm going to do is I'm going to make sure that my scale lines up. So if this is 0, this is going to be 0, and this is going to be 0, so everything lines up. So I'll put some values here. So for the first interval, or the first interval here, it's going to be between the values of 1 and 3, and everything in between, and including it. We have the hard bracket, so that means less than or equal to, greater than or equal to. Now the next set, we'll switch into a different color. This line here is going to be represented by this set. So we have between two, oops, let's change the highlighter. We have between the values of 2 and 6. And these are going to be rounded because we're having less than or equal to, or excuse me, less than or just greater than, but not equal to. So what we're looking for is the ones that they have in common. So I can't say there's any values at 1 because 1 is in the yellow line but not in the green. I can't say there's any values at 6, or common values at 6 because 6 is in the green but not in the yellow. But if we notice, the only times where they both have values is on the lines between 2 and 3. And what we have to do is we have to use the endpoints that are represented by each side. That hard bracket here becomes the end of the yellow interval, and this soft bracket here becomes the end of the green interval. So the answer to this is all of x such that x is between 2, not negative 2, 2 and 3. But again, with the second set, the second end of the interval, it's less than or equal to, so I have to make sure to include that as it was represented by the bracket. So let me go ahead and graph. We're now looking for the union of all values. So the first thing I'm going to do is I'm going to transfer here, and these values should look exactly the same. It's the same interval, but the difference in the answer comes in the difference between this notation here and this notation here. So as you see from left to right, the yellow and the green are exactly the same because I'm still graphing these two intervals. But the difference is the fact that I want all of the values. So whether they overlap or whether I don't, I see that in between 1 here at the bottom of the yellow and 6 at the top of the green, everything is covered. So the thing to remember is union refers to all values on either graph, everything possible, and intersection refers to only the ones that they have in common. And that's what we have to do when we have to tell the difference. So go ahead and pause the video and see if you can't find the difference, excuse me, the graphs in the intersection here and the union over here. So first of all, we have the two different intervals graphed on each line. The yellow interval is on the top line, the green interval is on the bottom line. But once again, when we want the intersection, we want what's in common. So what we're going to do is I'm going to look, the only places where they overlap between the yellow and the green is simply between the -1 down on the bottom and the and the 0 here at the top. So the only thing that they have in common is between -1 and 0. And this is the actual answer. The green and the yellow is just kind of a workspace, but this last graph is the intersection between the two. Now looking at the union wants everything. But this also asks for the intersection. Actually, this should have been the union, so we should correct that. Because that's asking for the same thing twice. So the union wants everything. So we're going to go here, and we're going to go here, and we're going to extend everything that possibly gets touched. Not only the overlap, but the points at the end on the left and the points at the end of the right. So this is the entire answer here. For solving inequalities and then representing the values on the number line, we simply have to remember the rules of algebra. The one difference between inequalities and equations is that when we divide both sides or multiply both sides by a negative number, we have to flip the signs. We have to flip the inequality. So let's do this as an example. I'm going to subtract 2x. We're going back to pre-algebra here. And this is now 2x plus 1, and this is -7 over here. Take the time to carry down the inequality. A lot of mistakes that people make is they simply kind of get lazy and they start to do this, where they add the equal sign in the middle because it's just habit. It's not an equal sign, it's actually an inequality. And then I can continue. So I haven't, in this problem, I haven't divided or multiplied both sides by a negative number, so I'm still fine. So my final answer is x is greater than -4. So when we put this on, again, x is greater than, that means I'm going to go that direction from -4. It's greater than, not greater than or equal to, so I need a soft bracket, and we go this way. And I didn't ask for an interval notation, but interval would have been starting at -4 and going on into infinity. But when I'm solving this one, we know to get x by itself, I need to divide both sides by -5. but now I've divided both sides by a negative number. So now where it once was greater than or equal to, now it's less than or equal to. And because it's equal to, we have a hard bracket at -3, and we shade everything to the left. And then if I were to do my interval notation, the bottom end would be -infinity, the top end would be a -3 with that same hard bracket. For this next one, we're still going to use the idea of common denominators, just like we did in section 1.2 or solving rational equations. So we're going to do that same idea here. Pause the video and see if you can't complete it. So solving rational inequalities is exactly the same as solving rational equalities or equations, where we got a common denominator of 72. This one needed a common factor of 12, this one needed a common factor of 8, and this one needed a common factor of 9. So once they're all over the same common denominator, then we cancel everything out and continue to solve. Lucky for us, we didn't have to multiply or divide either side by a negative number, so we continued to have the inequality be the less than or equal to. So 77 fourths, we can put that here. That's the same as 19 1/4. Either way, it's going to be less than, and I have the equal to, so it's going to be that hard bracket and going everything this direction. And as a reminder, this is starting at -infinity because it's less than, always getting the round bracket, and then 19 1/4, or you could have put 77 fourths on that side. Now when I look at here, I have two inequalities, so I actually have to set it up separately. So this means -3 is less than x minus 4, and it also means that x minus 4 is less than 6, less than 6. So first of all, solve both of these inequalities. Pause the video. So solving each one, we have now that x is greater than 1, but x is less than 10. So graphing this on the number line, this is actually an and situation, or what's known as an intersection. So what we have now is the fact that this is now less than 1, greater than 1, 2, 3, 6, and I ran out of number line, and 10 over here, and then it's up here, but remember, because this one did not have the equal to, it's going to be rounded. So in solving inequalities, we simply set them up separately. What if we have absolute values with inequalities? Absolute values that have less than are our and situations. Again, another sign of intersection. So what we actually have here is saying that x is less than 3 and x is greater than -3. Remember that any value inside the absolute value brackets can be represented by the positive or the negative to get to the absolute value of 3. So x is less than 3 and x is greater than a -3. So if I'm going to, similar to the video earlier, we had the green and the yellow, I'm going to place my number line. And I'm going to represent the first one. So we can think of this again. I usually now have them floating above, and I'll show you what I mean. Pause the video and I'll set this up. So I have these both set up with the yellow and green. Now, usually the test will not give you 3 lines to work this out. So what I do is I simply have them floating above. And an and situation, which is every time we have an absolute value less than a value, is when we're looking for the intersection between them. So as I see these floating above, the common values that they have here are -3 to a +3. So this is the actual answer here. So doing this again, when I'm setting up the absolute value, we have that it's still a less than or equal to. So we have that 3x plus 5 is less than or equal to 17. I can solve that one. Then we also set it up where I have 3x plus 5, and then we have the -17. But if I'm switching the sign, I'm also switching the sign. So please compare this one. This one is the opposite direction of this way, same as this one was the opposite direction of this one. We're switching the sign on the value on the left, or excuse me, the value on the right, and we're also switching the direction of the greater than, less than value. So pause the video and solve it, and then put them on the green and yellow number lines. So here are both of the solutions, and then I've got the number lines set up here. This is again looking for the intersection between the two. So as we put these together, I'm looking for the points that they have in common. They overlap on all of these points. So between -7 and 1/3, which is what 22/3 is, and a +4, these are the values that they all have in common. Now this is for when we have an absolute value less than. When we have an absolute value greater than, this is going to be our or our union situation. So we're going to solve these exactly the same way. So we have the absolute value of x is greater than 2. That means x can be greater than or equal to 2. Or x can be less than, flipping the sign and changing the sign on the number. So we have 0, 1, and 2. We have x is greater than 2 or equal to it. So I'm going to graph this way. We also have x is less than a -2. So I go this way. And in this situation, I'm looking for the union, so I'm looking for all points. If I was looking for intersection, this would have no solution. There's no place where these two overlap. But lucky for me, I want all of the union. I want everything here between the 2 points. Or I want everything beyond the 2 points, excuse me. We're going to solve this again. This is another greater than situation. But remember to isolate your absolute value. So divide both sides by 2 first. So we can set this up. So we have the absolute value of 3x minus 1 is greater than 10. And because it's a greater than, absolute value greater than, we have an or situation or union. So 3x minus 1 is greater than 10. And then we flip the sign again. 3x minus 1 is less than -10. Pause the video and graph it. So that leaves us with 3x minus 1 is greater than 5. And because, again, this is an or union situation, you're going to set it up for 3x minus 1 is greater than 5. And then we flip both of them. 3x minus 1 is less than -5. Pause the video and graph it. So solving these again, we have the intersection, excuse me, the union. So we're looking for all the values going this way or all the values go this way. We're not looking for any kind of overlap. So as we look at these final two problems, they look like they're being rearranged, but keep in mind that this is the absolute value is still less than, even though I know the greater than sign is pointing in a different direction. So when the absolute value is less than, this is going to be an and or intersection problem. And this one, oh, it looks like it's changed up, but no, it is. No, it is. Yes, it is. The intersection here, the absolute value here is greater than. So we are going to have an or union situation. And I will put the solutions up in a moment. This first one was the intersection, so it's going between -1 and 9. Which I have to extend the number line here. And this one, it's going all the way up to 9 over here. This one is going to be the union. I'll put up the answers in just a moment. And with the last problem, as a union problem, we have x is greater than 1/2, x is less than a -4, and talking about both intervals as they go from left to right on the line.